So we're dealing with class 7 in Elements of Mechanical Design, ME370, and the topic du jour is curved beams. So curved beams are a little bit different from just the standard beam or door handle type of situation that we have. And so we can see that here's a couple examples. There's curved beams that are in Shigley. This is section 318. You can see that there's this like little this hook that's been made out here, and I'm not sure what I would describe this thing of. I mean, this looks like it's almost kind of like part of a spring, maybe, or something along those lines. This looks like some type of machinery. Could be like a C-clamp or some type of a component within maybe a stamping, dyeing machine or something, or you have this like little elbow looking kind of bracket. Have this kind of little bracket right here, so we can see that there's a curvature right there, and or even this little piece, we might call this a strut, right? So it's got this little bend in it, and even though it has axial forces. So you think about what's special about this scenario, and what will always happen with the normal stress? That's the hint that I'm giving you. And the answer is that in all of these cases, we're going to have bending and axial at the same time. And so we have to address both of those things, both a simultaneous bend and axial going on here. So let's take a look at like one of these and try to see what I'm talking about. You see that this load is on this piece of 2,000 pounds going up on this part and down on this part. Well, that's going to tend to try to bend this section. But also just the act of it being there will cause an axial. And the way to really understand or to see this is to draw a free body diagram of it through this section, and you can see that it's going to have not only the bending, but it's also going to have the axial. The same thing true with this strut. So maybe I ought to like try to prove that to you by way of taking a little free body diagram of one of these things, right? To just draw it like so. Let's do this guy right here. We'll use this little space that's up above, and we'll make a little cut right here. And what we're left with is a force right there. There's the 2,000 pounds being applied to the thing. Here is going to be the section of interest. Right in there is going to be a equal and opposite reaction right there. It's going to be in the y direction. But now it also needs to balance, moments need to balance out. So the moment, let's take the moment about maybe the center right here, so we get rid of that force. And that thing is going clockwise, so this needs to go counterclockwise. So there's a moment right in there. So here we go. Right in that section, there's a bending moment and there's an axial force. And is it in tension or compression? It's obviously going to be in tension, right? It's pulling away from the thing. And also, if you go back to this guy right here, you can imagine these are pulling the thing apart. It's pulling, so it's going to cause both tension and it's going to have axial, and it's going to have bending. Now, that means that like that bending is going to cause tension here and compression here. So it's going to have an additive effect. The tension due to this axial is going to combine with the tension due to the bending, and there's going to be more bending stress on the inside. And then the compression due to the bending is going to be somewhat relieved by the axial tension here. So it's actually going to have less stress right here. So this is the spot where it's going to break. But wouldn't you already kind of intuit that? Wouldn't you already have the intuition that it's going to break that spot? We could also do the same thing on this, right? We could just take and cut right here. And we have that force onto there. Well, at this section, we need to have an equal and opposite. The forces need to balance out, and the moments need to balance out, right? And if you're questioning which direction that's going to go right here, you would see that this is going to try to go counterclockwise, so this would need to go clockwise. Did I say that right? Okay, so we're going to take the moment about this point right here, And this is the reaction right here. So yes, that's going to have a counterclockwise, so that better be a clockwise moment reaction right there. So once again, that moment is going to cause a tension here and a compression there. So the tension from this and the tension from here, so once again, it's going to break. It's going to have a larger stress due to tension right there, and its compression is going to be a smaller magnitude of compression. All right, so that's kind of like the big idea of this of doing a beam in bending, or a curved beam in bending. So we need to get orientation here for how we're of some of the geometry that's going to be slightly different. So we don't have the same condition for a bent beam, a curved beam, than we do from a straight beam when we're putting a bending moment on it. And it turns out this critical difference, which I'll answer down below, is the centroid does not equal the neutral axis. Right? And that's the critical thing that's going to be different. So I'm not going to go through the derivation here. I'm just going to give you like a tour through how the book set up with the variables and the main equations. But like we have this generic cross section of this generic curved beam area right here, and we see the all important neutral axis. The neutral axis is the axis of zero stress. Right, so looking at this one right here, it looks like compression is going to be on the outside and tension is going to be on the inside from that moment thing right here. And so zero is going to be right here. And they decided for some reason they're going to take the reference when they're going to use y is going to be this location that we're going to use as our reference, and is from the neutral axis. So just be aware of that. So some of the geometry, like things that we might already know, we're probably going to be given. We're probably going to be given that we have the outside radius, the outer radius, right there, right. So I have these two right next to each other. So this is not drawn on there, but RO is going to be all the way to out there from the center of the curvature, right? We got to make sure we know where the center of the curvature is. And then we also have RI is going to be the radius to the inner fiber. So these are going to be two things that we would probably know, and they didn't draw it over here, but here would be RI to get up to the right there, right? That's this cross section through this spot right there. Now we're going to have the height of the section. Right, so we could actually just calculate the height of the section. That's really the difference between RO and RI. All right, so that would just be equal to RO minus RI. We're going to have this distance from the neutral axis to the outside fiber. Now, that's something we're going to have to know where that neutral axis is pretty soon, right? But I could also write out that's going, we'll get to that. We'll get to that. And then we have the distance from the neutral axis to the inside right there. That's something we're going to know. Now, here's the important one. The radius, this is Rn. It's hard to see, probably hard to see on that video right there. That's an R subscript N. He's right there, and he's right there. Right, so there's to the neutral axis. You could tell from this, because it's a symmetric section, though, that the centroid is actually right here. Right here is like the midway point between RO and RI in this particular case, because it's symmetric. And you could see, all right. So there's the RC that I've written over here. Here's RC, and you can see that they have something called E. E is this distance between the two. It's the distance between the fact that Rn does not equal Rc. Like you could say that Rc does not equal Rn is another way that I could answer this. The critical difference between a curved beam and a straight beam. And then we have the moment. So here's our main equation. We have My divided by Ae Rn minus y. So you'll see that y appears in two spots right in there. This is equation 364 out of Shigley. So this is something we're going to go back to each time that we look this thing up, but become familiar with it. And so look at it carefully and get your orientation. All right. So let's look a little further into how we find that Rn. Now that it's not the centroid, we want to find this the neutral axis, and we do that. Here's the basic equation for the thing. It's the area divided by dA over R. All right, that's the big idea equation. We don't want to do any integration if we can try to avoid it, if at all possible. Right? I say compare this. Okay, so this is the location of the neutral axis for the curved beam. Right? So we take the overall area and we take the incremental areas divided by the radius to get to there. Compared to the RC is the integral of R dA divided by A. It's kind of interesting comparison to sort of make. This is a generic. This is always true if we were trying to find the centroid of the thing. So to apply this, we're just going to look it up in a table. But let's before we go to that, before we just jump and looking the thing up in a table, let's take a look for the most basic of things: a rectangular cross section, which we could have. We could have a curved beam that has a rectangular cross section. We could say, okay, so the area is just going to be the base, and so this is going to be base B times height. But we could find incremental areas, right? So if we had an incremental area that looked like that right there, would be B times dr, right? Here would be dr, like little incremental r's onto the thing, right? So we're using r, we're measuring it from here, but here's the incremental of the r's. If we plug this in to this thing right up here, we'd get Rn is equal to A divided by, I won't rewrite the equation. The equation's right there, so I'm going to give myself some more space. And I'm going to say that's B times H, right? That's the overall area of the thing. And it's divided by the integral from Ri to Ro of dA, which is B times dr, divided by R, right? And if you do that, you find out, well, this B is going to cancel out. That's a constant, right? That base is a constant to the thing. And all you're left with is H divided by the natural log of Ro over Ri. Well, if you look it up in table 3.4, you're going to find that's what they just told you, Rn. So it's kind of a proof. I didn't derive the thing all the way, and we don't need to go through this process each time because it's done for us in this table 3.4, but that's where it comes from. That's the big idea. And you could do something similar. And the most common ones that we'll have is a rectangle and a circle. And you can see, you can get the location or the radius from the center of curvature to the centroid easy enough by taking the inside radius and then 1/2 of the height. And obviously that's going to be RC. Same thing true for the circle. You could take the inside radius, and they're calling the radius of this circle itself capital R, right? And so then you can see what the radius to the neutral axis of the circle is. But let's take a look at the other things in the book, the other sections in the book right here. So there you go. Here's our table 3.4, and you can see here is our setup for different cross sections. I already showed you the rectangle. Here's sort of a trapezoid kind of shape. Here's like a little T shape, and here is a circle. And here is like this unequal I-beam setup right here. Now I'm going to point out a mistake that was in the book that I've noticed a while back, and I've looked through other versions and I think they keep making the same mistake. So let me see, I'll close down my comment, and I just want to highlight, if you look at the pattern of what's going on here, notice that for whatever reason the thickness of this, we'll call it a flange on this outer one, the TO, and this is the flange of the inner one, and this is T by itself, and no subscript, is actually the thickness of what we call the web, right? But if you look at the pattern of what's going on, like TI, BI minus T, TO, BO minus T, and then H times T, right? These are all like really the areas that that's what this top part is. And then we take a look at the yeah, I just want to say this the right way. BI, which is this width right there, is a natural log of Ri plus T divided by Ri. And let me double check on something, because I'm forgetting what is wrong with this equation, but I know I happen to know it's wrong, and I didn't write it down here. I really should have written it down. So be on the lookout. Maybe we could go back up to the square. I think the square helps us know, and it's not the square that helps us. It's maybe this guy that helps. The BI is natural log of Ri plus C1. Yeah. I think it's this guy right there. That's the one that's wrong. That should be TI, because it makes no sense for it to be this thickness. It should be Ri plus TI, just like this is RO minus TO, right? Divided by Ri plus TI, right? So this thickness doesn't matter. So this guy right here should be TI. So that's a mistake that's in the book. It gets carried through in many different sections. I know this to be true because if you calculate these values right here, you'll get some nonsensical stuff. So it's something that I wanted to point out. Let's keep going with our thing. So this is our introduction portion of the video. I'll do examples after I get to this part where I am. All right, so here is the equation that we just used previously, but we showed with the y onto the thing. But we note that where we really care about is the inner surface and the outer surface, and these are equations 365. So if you just jump to this equation during an exam, you're going to be frustrated. So be on the lookout for that. So instead, what we could do at the outer or the inner surface, we could say that y at the inner surface, at the inner, we could substitute Rn minus Ri and say that that's equal to Ci. We could also say that y at outer is equal to Rn minus Ro, and that's actually equal to minus Co right there. So if we substitute those back in, one of the things that's going to be nice for us is when the Rn is going to cancel out in there. That's going to help us. And what we end up finding is we get the moment times Ci divided by AERI. And over here we get minus the moment CO divided by AERO. And so those are the main equations that we're going to use. But remember, these are only for the bending stress, right? So these only came to the bending stress. So the combined stress that we'll often do, and we have to be careful to use these. So make sure we'll put a star next to it and say, caution. Don't just write these down. You actually have to decide whether there's tension or compression going on. You still have to kind of think your way through this and not be a plugger and chugger of numbers, because you could instead, this could be compression instead, right? Or the loads on it could be opposite from what you're saying. I'll point this out here in a second. But from a typical scenario, these are the equations that we're actually going to use right here, where we're going to say that AE over RO, right? So we'll take this as the bending part of it, and we'll add. So this one, these equations are really only for the condition, right? Let's see, we'll show like this right here, where we have this right there, right? So that we're going to take and we're going to analyze that section right here for what the stress is going to be. But mind you, this was tension, and it's going to combine for the inside to create a higher stress, whereas this is tension, that's going to be compression, and so we're going to have a lower compression that's going to happen onto this guy right here. You could have the scenario, mind you, where we go that direction, right? We could have compression being placed on here, right? So still the inner is going to have a larger stress. It's going to have compression right here, and it's going to have tension to the outside, right? Now, I think I accidentally wrote C. That should be a CO, lower subscript CO. I was talking and writing at the same time, right? So just be careful. This is for like the generic situation, but make sure you'll see this. So in the book, there is an example that they walk through, and I'm not going to walk through it. I'm going to do other examples, but I'll leave it up to you. But here are the results of it. Kind of interesting type of thing. And because we have our main equation is this one right here with the y and the y. That really describes, remember, once again, that y was the location. Let's see, we go back to the original sheet. Is it available, or did I move it over? Right here it is. That y was really that thing that was pointing inwards and at the neutral axis right there. So as we're moving along through there with that y, what we have is really sort of a hyperbolic type of distribution, right? Because we have a y up here and we have a y that's buried inside there. And so it's like a hyperbolic distribution. Now remember from the class 2, we talked about having axial as a uniform distribution, and bending had a linear distribution, but it doesn't here. In this case, it has a hyperbolic distribution of stress. And you can see it from the results of this example that it has this type of shape that's going on to it. I think I might want to call it parabolic, but I think it is. My recollection is hyperbolic, but I don't want to. I don't want to stick to that 100%. But this one also shows that it has superimposed the axial that's taking place on top of that, and as an interesting sort of confirmation of that. I like to do FEA anywhere I can. I went ahead and did a FEA of this example, and you can kind of see this distribution through this cross section right there. Here is a plot of those stress values along for nodes that are along this line right here that I created, and you could see how they match up with the shape of this, and also the magnitude of the results. And for whatever reason, I made an animation of the thing, so we could just like take a look at the thing. But you could get the idea that is like in this case, you see that the 0 was between these two versions of blue. Right in there. So this is the next. We're going to do this example as the next problem. This will be a different video. There's one last thing I wanted to point out in the book, is that one of the things that we're going to need to calculate for this is E. E right there, and E, that's, you notice that Rn is not in here. So the thing we're actually going to calculate most often is E, which remember is this guy right here. E is equal to the difference between the centroidal radius and the radius to the neutral axis. And that's the important thing, right? That's really the fundamental difference that's between a curved beam and a non-curved beam. It says E right in there. But we need to find Rn, and we find Rn from going to table 3-4. But a simpler way, not maybe simple, but a way to approximate that, if we didn't have it or if we were too lazy, if you know the cross-sectional moment of inertia of that section by itself, and you divide it by RC, and you divide it by R, and you divide it by A, that will give you an approximation. And so this is equation 366. So it's something else I wanted to point out. So a quick and simple approach to finding E, or confirming that you're in the ballpark, which was kind of an important thing for me to do when I got to doing a problem that was like this, where I used this cross-section. You might ask, why would you ever use that cross-section? Because that's very similar to what a lot of C-clamps are. Now, I don't have any C-clamps up here with me, but I often will bring one to class, or we might want to do a problem with a C-clamp and then try to use this thing, but getting some kind of crazy number. But then, like, I located and found where the mistake was in Shigley, and then I can confirm it by using this simplified this approximation. I was able to confirm, yep, that's the one that's messed up. And then you can also do an FEA of the thing that you calculate by hand, and you can find that mistake. So there you go. That is our 26-minute introduction to curved beam bending. Hopefully this will be useful to people who want to go back and see what the deal was if I confuse you during a lecture.